All right, good morning, everyone. So let's start our lecture on heat and calorimetry. We're sort of moving a little bit away from gases, but it's still related to what we've learned so far. So far in our lectures last week, we started by defining what temperature is as being the perception of hotness or coldness of an object, and then we related temperature to the actual movement of the atoms making up the object. And so we've seen that the temperature is actually is measured by the average kinetic energy of the molecules. And then we developed a model using ideal gas laws, whereby we've seen that the total energy of all the molecules depends on the temperature of the gas as well as the number of molecules in the gas, and that gives us the internal energy of the ideal gas. So this equation we derived in our last lecture when we talked about ideal gases, kinetic theory of gases. This only holds for ideal gases. Because we sort of use the assumptions for ideal gases and the ideal gas law to derive this equation for internal energy. But the concept of internal energy is that it's simply the total energy possessed by all the molecules making up the ideal gas. So the concept of internal energy can be extended to solids and liquids as well, because solids and liquids, they also consist of molecules and atoms, and the molecules and atoms are also vibrating as a function of temperature. So higher temperature, the faster the molecules and atoms vibrate. So so in this lecture, we will consider the internal energy of objects in general, including solids, liquids, and of course gases. So say you have a pot and you put it over a flame as shown here. Well, we know from experience that the pot will heat up, right? And so energy will transfer from the flame to the pot, and as a result, the pot will heat up. So the process of heating up is called heat. So the process of heating up is a result of the transfer of internal energy from the flame to the pot. So in this case, the energy transferred from the hot flame to the cold pot, the act of transferring the internal energy is what we refer to as heat. We'll use the capital symbol Q for heat. And the reason why energy is transferred from the flame to the pot is because there's a difference in temperature between the flame and the pot. So heat will transfer, there's a transfer of energy, or heat will transfer from the hot object to the cold object until thermal equilibrium is reached. When we say thermal equilibrium, we mean that the temperatures of the two objects involved are equal. Right, so heat, it's the process of transferring internal energy from one object to another. But we also use the term heat to refer to the amount of energy that is transferred by itself. Okay. So heat is both a verb and a noun, if you like to think about it this way. It's the transferring of energy, at the same time it's the amount of energy that's transferred. So we use the term heat interchangeably, but it's also sort of related, right? Because the amount of energy transferred depends on the difference in temperature between the two objects. So since it measures the amount of energy that's transferred, so let's look at the units for heat. The SI unit is the joule. It's the same unit as energy, like kinetic energy or potential energy, because heat itself is energy, right? It's the amount of energy, internal energy that's transferred from one object to another. So its SI unit is the joule. There is one other common unit used for heat, which is the calorie. Okay, calorie with a small c, and the conversion factor between calorie, which is the non-SI unit, to joules, which is the SI unit, is given in this slide. To complicate matters a little bit, there is also this calorie with a capital C, which is most commonly used in measuring the energy released by food when food is burned or digested or metabolized. It's simply, the calorie with a capital C is simply equal to 1,000 calories with a small c. Okay. Right. So to convert calorie with a capital C to joules, it's essentially multiplying by 1,000, and so you have these kilojoules in the conversion factor from calorie with capital C to joules. Yeah, and it's usually what you see at the back of food packets, which tells you, the number of calories for that particular food. It's measured by how much energy is released when the body metabolizes that food, and the one you see there is the one with capital C, which is equal to 1,000 calories small c, or 4.186 thousand joules. Right. Okay, so just clarification with units, and so far we've only just defined heat. So just to summarize the different terms that we've learned so far, when we say temperature, it's the measure of the average kinetic energy of the molecules. It's usually what we measure using a thermometer. Internal energy, it's the total energy of the molecules making up the objects, regardless of whether it's a solid, liquid, or gas. And when we say heat, it's the internal energy, the amount of internal energy that's transferred. And internal energy is transferred from the hot object to the cold object, or high temperature to low temperature. Right, so thinking about what we've discussed so far, if you have then two objects, one cold and one hot, and you put them together, then energy, heat will transfer from hot to cold, and as a result, the temperature of the objects will change. So this relationship tells us that the amount of heat that's transferred will be directly related to the change in temperature of the two objects. Right? So Q is equal to C delta T. C, capital C here, is called the heat capacity, which is defined as the amount of heat needed to raise the object's temperature by 1 degree Celsius. And it's equal to the mass times a small c. It's getting a little bit confusing because we have capital C and small c, but then if we substitute the definition for heat capacity to the definition of the amount of heat needed to change the temperature, we have Q equals mc delta T. And this is the most common form of the equation that we'll find in the textbook or in the internet. So going forwards, we will usually just use this form. The amount of heat needed to change the temperature of the object as a result of energy, internal energy being transferred from one object to another. Right, so in this form, we can see a direct consequence of heat being transferred. The direct consequence of heat being transferred is the change in temperature. And so this kind of heat is called the sensible heat. Later on, we will learn a second kind of heat. But when we say it's called sensible heat, because we can sort of sense the effect of heat being transferred from one object to another. And the effect of that heat transfer is the change in temperature, right? So let's just define, before we look at an example and before we go much further, let's just define each of these terms in this equation so that we're clear what they all mean. So Q, that's the amount of heat that's transferred. It's measured in joules, as shown in the square bracket here. Mass, that's the mass of the object whose temperature will change, right? If heat is transferred to some object, the temperature of that object will change, and it depends on whether you have more mass or a little bit of mass. So M is the mass of the object whose temperature will change, of course, measured in kilograms. So delta T, that's the change in temperature, how much it measures, how much the temperature will change as a result of heat or internal energy being transferred to that object. Right, just a reminder, we've learned this before, but I'll just remind you that if you're calculating the change in temperature, you can either calculate it in degrees Celsius or Kelvin. Oh, sorry. Yeah, either calculate it in degrees Celsius or Kelvin, but if you're getting the change in temperature, Celsius is equal to Kelvin in change in temperature. Right, so pretty straightforward and pretty logical variables here. Now the small c, we haven't encountered the small c yet. The small c is called specific heat. That's measured, again, the units are given in the square bracket here. And the specific heat is a property of the material. It's a material property that influences how much that material's temperature changes as a result of energy being transferred, either absorbed or released. So let's look at the specific heat in more detail, what it is practically. A specific heat, small c, is defined here. As I've mentioned earlier, it's a property of the material, and you can see the formal definition of specific heat in this first bullet point here. But in practical terms, specific heat is a measure of the resistance of the object to change in its temperature. So you can think of specific heat as something like thermal inertia, or the counterpart of friction, right? Friction is for moving objects. For heat and energy, heat being transferred, you can think of specific heat as thermal inertia or thermal friction, if you'd like to use that term loosely. Meaning, the lower the specific heat, the easier it is to change the temperature of that object. Okay. Right. Because the lower the specific heat, the less the resistance to the change in temperature of that object, and therefore the easier it is to change that object's temperature. Okay. And since it's a property of the material, you can look it up in some table. For example, this table shown in this slide. So if you compare, for example, a pot, if you make a pot and you say make the pot out of steel compared to making the pot out of aluminum, right? Which pot will heat up faster and therefore cook the food faster? And this is why pots are made up of steel. Steel has a lower specific heat compared to aluminum. And so steel, given the same inputs of energy, steel will heat up faster, will change its temperature faster because it has a lower resistance to change in temperature. Right? Of course, if you want a pot that heats up more, even faster, you can use silver, but that's again a question of cost, right? Okay, is the concept of specific heat clear, or at least right. So some few conceptual questions here. It takes about 2 minutes to raise the temperature of an iron pot to boiling temperature, but it takes less than 1 minute to raise the temperature of the same amount of water to the same temperature in a silver pot. So which one will have a lower specific heat, iron or silver? Right, the lower the specific heat, the faster it is to change its temperature. So given that you are putting the same amount of energy and reaching the same temperature, silver will have a lower specific. And if you again look at the table, you will see that silver indeed has a lower specific heat compared to iron. So different substances have different specific heats because it's a property of the material. Okay. How about if you have 1 gram of water and it requires 1 calorie to raise the temperature by 1 degree Celsius, and you have the same amount of iron, raise that to the same 1 degree Celsius, but it takes only 1/8 as much energy. So which has a higher specific heat, water or iron? Yeah, water, right? So the higher the specific heat, the more difficult it is to change that substance temperature, and therefore that object will need more energy in order to change its temperature by the same amount as the other substance. Okay. Good. All right, any questions so far about the concepts? I think we're okay. Then let's look at a numerical example. Looking at sensible heat. Again, sensible heat is the heat associated to change in temperature, because change in temperature is what we can sense. Here, 30 grams of mercury is cooled from 280 kelvins to 100 kelvins. We want to calculate how much heat is transferred given the specific heat of mercury here. So it's a relatively straightforward application of the equation, right? The temperature changed, so we're able to sense the effects of adding or of transferring heat, and that's given by Q equals mc delta T. We want to find Q. M is the mass of the object whose temperature changed, which is mercury, 30 grams converted to kilograms, 0.03 kilograms. C is the specific heat of the object whose temperature changed. The specific heat of mercury is given. And then you have the change in temperature. So change in temperature, that's the final minus the initial temperature. Okay, so that will give you a negative heat. The amount of heat transferred is negative 756 joules, right? So the negative sign here means that the object or mercury lost energy. So when you're calculating heat, amount of heat, and you get a negative sign, the negative sign means that it's a loss of energy, okay? And that is why the temperature decreased, right? It went from 280 Kelvin to 100 degrees Kelvin because of the loss in energy. So you can very well just calculate Q is equal to MC with an absolute value in temperature and not have to worry about which temperature you use as final or initial, although it's easy to determine that, right? But you can always calculate the amount of energy or heat transferred as a positive number, MC delta T, and then whether it's energy lost by the object or energy gained by the object can be answered by looking at the context, right? If the object's temperature decreased, then we know that the object lost energy, even if your calculator is giving you a positive number for the Q. So always look at the context of the problem to determine whether the object lost energy or gained energy as a result of heat transfer. All right. Cool. So we've seen here that when energy is transferred, the temperature of the object will change. But sometimes the temperature doesn't also change. Sometimes when we heat up an object, the object will also melt. So a classic example is ice. If you heat up ice, ice will melt into water. And when you heat up water, water will boil into steam. Or we can do the other way around. When you cool down steam, the steam will condense to water. And when you cool down water, the water will freeze into ice. So we've learned the different phases, solid, liquid, gas. And when you're changing from one phase to another, you have a phase change. And intuitively, we know that for ice to melt, we need to heat up the ice, right? We need to put some energy into the ice in order to melt it. So in other words, heating can either result to a change in temperature. Okay? If the object absorbs energy, it can either increase in temperature or it can undergo a phase change. So let's look at the case now where the object undergoes a phase change. In the earlier slides, we looked at the case where heat is added and the consequence of that is the change in temperature of the object. So now let's look at heat is added and the consequence of that is a change in the phase of the object. So, so to change the phase of the object, either from solid to liquid or liquid to gas, extra heat is required, right? So the extra heat required is to either break the bonds in the material, the molecular bonds in the material need to be broken during melting or vaporization, right? So when you're going from ice to liquid water, the heating up of ice goes into breaking the bonds of ice so that you have water in the end. So melting and vaporization requires extra energy to break the bonds. The other way, the reverse way of phase change, when you're going from gas to liquid or liquid to solid, you have condensation or freezing. Extra heat needs to be taken away. Extra heat is needed to form the bonds in the molecules. So in the case of phase change, the amount of heat, Q, is equal to M times L. Right? And we will define each of these terms again. Q is once again the amount of heat measured in joules, the amount of heat that's either put into the object or taken away from the object. M, that's the mass of the object that's undergoing phase change. So if water is boiling, then it will be the mass of the water. We usually assume that the mass of the water will be equal to the mass of the resulting steam. Right, now this L in this equation, we haven't met this L yet. So this L is called the latent heat. Latent heat measured in joules per kilogram. Okay. So this amount of heat required for changing the phase of the object is called latent heat because latent means hidden, right? Unlike the change in temperature, we can easily sense it, right? Because the object is becoming colder or the object is becoming hotter. And that's why it's called sensible heat when there's a change in temperature. But during a phase change, it's hard to sort of detect whether whether liquid water is slowly freezing into ice, or whether water is boiling into steam. And that's why the heat associated to phase change is called latent heat or hidden heat. Now, latent heat, L, is a property of the material as well. So similar to specific heat, latent heat is a property of the material, but it's associated to the phase change of the material. The material can have a latent heat of fusion. There are two kinds of latent heats: latent heat of fusion or latent heat of vaporization. Latent heat of fusion is associated to the phase change going from solid to liquid or liquid to gas. Liquid to solid. It's like you can think of the molecules and atoms that are fusing together as they freeze from liquid to ice, and you call that latent heat of fusion. Incidentally, the heat required to freeze material is equal to the heat required to melt the material, and that's why latent heat of fusion refers to both melting and freezing. So you use latent heat of fusion if the phase change is either melting or freezing. Latent heat of vaporization, you can pick up their vaporization. That means when the object goes from liquid to gas, or this is evaporation, or gas to liquid, in which case condensation. Right, so if the object is evaporating or condensing, use the latent heat of vaporization. Okay. And as before, Q can either be positive or negative. It's positive when it's gaining, if the object is gaining energy, such that melting or boiling. Okay, so you heat up the ice will gain energy, and that causes it to melt. Q is negative when heat needs to be taken away from the object, so that the object loses energy. And in that case, if water loses energy, it will freeze into ice, or if steam loses energy, it will condense into water. All right, is that okay so far? Not so confusing anything. All right, so we've first defined what heat is, and then we have enumerated, we've looked at the two kinds of heat: sensible heat, Q equals mc delta T, and then now latent heat, Q is equal to ml. Now let's combine these two kinds of heat by looking at this graph and using ice, the phase change of ice from ice to steam. So we're all familiar with ice and water and steam, and that's why let's use that as a model for combining sensible heat and latent heat. So in this graph, we start with ice, okay? And we look at the temperature of the substance of the object. So y-axis gives us the temperature. Let's look at the temperature as heat is being added to the object. So the x-axis gives us the amount of heat that's added, or that's essentially Q. Okay. So let's start with ice. It's just all solid, and ice can have temperature below 0 degrees. In this particular case, it starts at -40 degrees Celsius. We add heat into ice. So heat is added, and as heat is added to ice, the temperature of ice will increase, right? Okay. We've learned that if you have an object and you heat that object up, its temperature will change. If the object is absorbing the heat, then its temperature will increase. But notice how the temperature of ice increases only up to 0 degrees Celsius. Okay. Right. When the temperature of ice reaches 0 degrees Celsius, the ice starts to melt. Okay. And hence you have water and ice coexisting together. So we call this 0 degrees Celsius. We call this the melting point of ice. Okay. So melting point, it's the temperature for which the solid starts to melt. Okay. As the solid starts to melt, you have two phases existing, liquid water and solid ice. Now, any input of heat in this point, once the ice has started to melt, any input of heat goes into the melting process. And so until ice is completely melted. So notice here how the temperature is constant at 0 degrees Celsius during melting. Okay? Because any heat added during melting goes into melting ice into water rather than increasing the temperature of the water and ice mixture. Right? So once all of the ice have melted into water, it's this point here. All ice have melted. Once all of the ice have melted into water, any heat that's added to the water goes into increasing the temperature of water, right? So it's all now liquid phase existing. If you add heat to water or all liquid, then the heat added goes into increasing the temperature of water, but the temperature of water increases only up to a certain point. So temperature of water increases only until the point where the water starts to boil. That temperature where the water starts to boil, in this graph, it's 100 degrees Celsius. This temperature is called the boiling point. So the boiling point of water is 100 degrees Celsius. That's the temperature where the water starts to boil. Once water has started to boil, any heat added to the boiling water goes into changing the phase of liquid water into gaseous steam. Right. So just like melting, during melting, the temperature of the water and ice mixture didn't change. It stayed at the melting point, 0 degrees Celsius. During the boiling process, since all of the heat goes into changing the phase from water to steam, the temperature of the boiling water will also remain constant at the boiling point temperature, which is 100 degrees Celsius. So none of the heat added goes into changing the temperature. Instead, all of the heat goes into changing the phase from liquid water to gaseous steam. Right. So until such a point when all of the water have boiled out into steam. So all water is converted to steam. Right? And when you only have steam or water vapor, gaseous form of water, then the heat added to steam will then cause the temperature of the steam to increase. Does that make sense? So adding heat to the system either increases its temperature or changes the phase of the object. And you can also do the reverse process, right? You can also start from steam, take away heat, right? In the reverse process, instead of adding heat, you're taking away heat. So if you start from steam and you take away heat, then steam will change, will decrease its temperature up to the condensation point, in which case you have condensation, change of phase, and any heat removed will condense steam to water, right? If you remove until all steam have been converted to liquid water. If you further remove heat from liquid water, the temperature of liquid water will decrease up to the freezing point, 0 degrees Celsius. If you take away heat, then the water starts to freeze and you have this water and ice mixture until all of the water have frozen to ice. If you take away heat further, then the temperature of ice will continue to decrease. So this graph is either adding heat will be the forward direction, taking away heat will be the reverse direction. Okay. Good, clear enough? Okay. Right, so it's quite easy to notice when you should use this equation Q equals mc delta T and Q equals ml. Notice that the temperature increases when the object exists in a single phase, right? So when the object is purely solid, purely liquid, or purely gaseous, then any heat added goes into the change in its temperature. So you use Q equals mc delta T if the object exists in just a single phase, whereas during phase change, when there are two phases existing, like liquid water or solid ice, or liquid water and gaseous steam, then you use Q equals ml because you have a phase change. The heat added goes into changing the phase. All right. Clear enough? Okay, let's look at an example then. So steam burn, it's often said steam burn is more dangerous than burn from water, just water at 100 degrees Celsius. So in this example, let's see why. By calculating the amount of energy transferred to the body, to the skin, if 1 gram of steam cools from 100 degrees Celsius to 36.5 degrees Celsius. We're given here the properties of steam, latent heat of vaporization, and specific heat of water. Right, so the strategy here is, we're given here 1 gram of steam. It's at 100 degrees Celsius. So that means it's at this point here, steam at 100 degrees Celsius. Right, so steam at 100 degrees Celsius, it condenses. Condensation. So it condenses on the skin. It will release energy to the skin as it condenses until all of the steam have been converted to water or condensation on the skin. Then the water would still be initially at 100 degrees Celsius, right, at the boiling point of water. Right, so when all of the steam have been converted to water, water will start at 100 degrees Celsius. It still needs to go down to 36. So 36.5 degrees Celsius is the temperature of the skin. So the water needs to lose this additional energy in order to bring down its temperature to the temperature of the skin. Right, so there's a change in temperature there. So that's the scenario there. So overall, the steam will have to release energy as it condenses to water. Okay? The energy released by steam as it condenses to water is given by Q equals mLV, vaporization, latent heat of vaporization. Right, we're given the mass of the water, of the steam, and latent heat of vaporization. Again, the negative sign means that heat is released by the steam, from the steam. Right, once the steam has been converted to water, water is initially at 100 degrees Celsius. Energy is then released as water cools down to skin temperature, which is 36.5 degrees Celsius. Right, since there's a change in temperature, the amounts of heat released will be the MC delta T equation. It's the mass. So the assumption here is the mass of steam would be equal to the mass of the water, because all of the steam has condensed to water. Right, times the specific heat of water and the change in temperature. Again, the negative sign means that water releases energy. So the total energy released as the steam condenses and goes down to a temperature equal to the skin will be the sum of these two energies released. Where will the released energy go? The released energy is transferred to the skin. So in effect, the energy transferred to the skin is the sum of these two energies released as the steam condenses and changes its temperature. Right? So that's why steam burn is more dangerous, because condensation, the process of phase change or condensation, releases more energy compared to just simply lowering the temperature of hot water to the temperature of skin. Right. Cool. Any question about this problem? Right. Good. Okay. Right. So we've learned how to use Q equals MC delta T and how to use Q equals ML. Now we've been saying that if you have two objects at different temperatures, say object A is at a higher temperature compared to object B, heat will transfer from the hot object to the cold object. If we consider that our system is isolated, meaning no heat can escape to the environment or to other objects, and the interaction is just between objects A and B, then conservation of energy requires that whatever heat is lost by the hotter object should be gained by the colder object. Right? Or in other words, heat lost by the hot object should be equal to the heat gained by the cold object. So using the concepts of the conservation of energy, right, which we call calorimetry. So calorimetry is just a term referring to the conservation of energy, where heat lost by the hot object is equal to the heat gained by the cold object. We can use that concept of conservation of energy together with sensible heat and latent heat to solve a wide range of more complicated problems. For example, in this question here, you have a 0.5 kilogram chunk of ice. It's initially at negative 10 degrees Celsius. And it's placed in 3 kilograms of tea. The tea is at 20 degrees Celsius. And at what temperature and in what phase will the final mixture be? And we, in the concept of conservation of energy, we ignore the heat flow to the surroundings, meaning the tea and the ice, they're a closed system, so that whatever heat is lost by the tea, which is at a higher temperature, goes into the ice, which is a negative lower temperature. Right, so how do we approach this problem? So I've already sort of gave an overview of what will happen. The tea, it's hotter, so it will lose energy. The lost energy will go to the ice. We sort of have an intuition that ice will melt, right? Because it's colder compared to the tea. But then we want to know what's the final temperature and whether the mixture will still be liquid. So we have to figure out how much energy the ice needs to melt. Okay. And then we also need to figure out whether the hot tea can indeed release enough energy to fully melt the ice. Because if the hot tea doesn't have enough energy to fully melt the ice, then you'll still have small chunks of ice floating on your tea, right? And then if there is some leftover energy, that will go into heating up the ice and tea mixture. And so that will allow us to find the final temperature. So does the approach make sense? Yeah. Because the first step is sort of like visualizing what's happening. And then the next steps are essentially just applying the heat transfer equations. So the first one, we have to figure out how much energy the ice needs in order for it to melt, right? So the ice starts from -degrees Celsius. We've seen from the graph that before the ice melts, it needs to reach the melting point, right? So from -10 degrees Celsius, the temperature needs to increase to 0 degrees Celsius before it can melt. Right? Once it's at 0 degrees Celsius, the ice starts to melt. Okay. That means that for ice to melt, you have to raise its temperature from -10 degrees Celsius to 0 degrees Celsius. You need heat to raise the temperature of -10 degrees Celsius ice. And then you have, you again also need heat to do the actual melting. Right. So this one is for the actual melting of the ice. Right. The mass of ice is given, specific heat of ice is given. The change in temperature, you need to reach 0 degrees Celsius in order for ice to melt. So that's your final temperature is 0 degrees Celsius. You're starting from a -10 degrees Celsius ice. Okay. Right. Once ice has reached 0 degrees Celsius, then it can start to melt. Yeah, so you have this latent heat of fusion. Just a note, that's a kilojoules, so that should be 333,000 joules per kilogram. Right. So then you determine how much heat the ice needs to melt, first by raising its temperature to 0 degrees Celsius and then melting. Now for the tea, do we have enough energy from the tea to melt the ice fully? The tea starts from 20 degrees Celsius. So it's not starting from boiling point, or it's not starting as steam. Therefore, the energy it releases is just mc delta T. So its temperature should just be lowered to starting from 20 degrees Celsius in order for it to release energy. So mass of tea is given, specific heat of tea, which is that of water, is given. And then the change in temperature of tea, this is the 20 degrees is the initial temperature. Well, if all of the heat of the tea goes into melting the ice, we assume that the heat of the tea will go down to 0 degrees Celsius.
Should it be?
Yeah.
Should it be 20 minutes or should it be 3?
Oh, sorry, third, yeah. Thank you. Don't know where the 20 is temperature. 6. Yeah, I think you'll still get 251,160. It was just a typo on my part. Right, so notice that the tea will release a higher amount of heat, a higher amount of energy compared to how much the ice needs to melt. So that means that the tea is able to fully melt the ice, and then there's still some extra energy left. After melting ice, there's extra energy left. So you sort of have then, you sort of conclude then that the final temperature of tea will not be 0. Because if we assume that the final temperature of tea is 0, then it will release 251,160 joules. but there's yeah, but it's so much more energy released compared to how much ice needs to melt, and therefore the final temperature should be above 0. So how to figure that out? Okay, there is some leftover energy, so the energy released by the T is that one. The energy needed by ice is just this one, smaller energy. So there will be a leftover energy of 74,160 joules, right? After T has melted the ice fully, there's still some energy left. This energy left goes into heating the ice and T mixture. Since you're changing the temperature, it will be MC delta T. The equation to use is MC delta T. Right, we're very far away from the boiling point, 100 degrees Celsius, and it's impossible for the T to freeze because we have extra energy that's left over after melting the ice. Okay. So to find the temperature, we use the leftover energy. Okay, that raises the temperature of the ice and T mixture. Notice how I use 3.5 kilograms here. This is the mass of the melted ice plus the T in combination, right? Because it's the mixture that increases in temperature. That gives a change at temperature 5 degrees Celsius. Any question about this example? Right, you will have practice with similar sorts of problems in the workshop. But if you have no questions, this ends our lecture on heat and calorimetry. And tomorrow we will start talking about heat transfer. So have a good day, everyone.